Hello, Mindsetters, and thank you for joining us. This is your favorite show, Learn Extra Live, with me, AB Abraham. I hope you're having a chilled Tuesday. It is the 13th of August, 2013. So I hope you're chilled up, had a nice day at school. If not, trust us, we're here to twist and turn your mood and make sure that you learn more and learn extra with us. I'm with Phil. How are you, Phil?
I'm great, thanks, and you, Abraham?
I'm feeling good. It's a good Tuesday, so I have no stress. I can't complain.
Oh, good. If you can't complain, then I can't complain, and we can learn together.
Complaining doesn't solve anything. It causes more stress and worry.
Absolutely. Let's just sort out the problems.
All right. Let's just stick to what makes us happy. What are we doing today?
Okay, well, what's making me happy today is we're talking about vectors and scalars. Now, these are two really strange words, but today I'm going to make you feel nice about scalars and vectors. Scalars and vectors really don't need to be a challenging subject, and I'm going to break it down really nice and easily. A lot of the grade 10s have reached this now, and I'm going to break it down further for them and make it a lot easier.
Well, if you still have some questions after all that we're going to be doing, because for some, it's just going to be a revision, make sure that you highlight us on Facebook, like our page, and if you have liked the page, also share it with your friends. Our page is facebook.com/learnextra. We have currently over 500,000 likes on Facebook, 50,079 likes. So the family is growing strong and big, and we are helping one another over Facebook. Second thing that you need to know is that you can follow us on Twitter at LearnExtra, and lastly, download your notes on learnextra.co.za/live. That's how you do it. It's all for free. I'll also post the first link on our Facebook page. But for now, let's learn.
Okay, great. Well, we're going to jump straight into vectors and scalars. Now, that beautiful quantity earlier, over 50,000 likes, guys, on Facebook. Get in there, bring your family, bring your friends, bring them in. We're going to talk more about those quantities. Now, those numbers is what it's all about today. A lot of you might say, okay, well, Phil, this is way too much maths for me. But really, it's just about dealing with numbers and saying, okay, well, I know what I'm doing when I'm dealing with numbers. Now, vectors and scalars are just dealing with two different types of numbers. So what we're going to do today is try and figure out what the difference is between the two. Now, let's take a look and see what is on the menu today. Okay, some of this is revision, like Abraham said, and then we're going to start dealing with some scalars and some vectors. Now, first of all, we're going to do a little bit of revision of scalar quantities. Now, you might say, Phil, I've never heard of a scalar before. Or if you have, you're kind of like, scalar, my memory's not serving me right. We're going to remind you what's happening over there. So, scalar quantities. Now, there's a lot of words inside here that might seem a little bit intimidating, but I'm going to hold your hand and I'm going to walk you right through them, so don't worry about it. Okay, so we're going to revise the scalar quantities. Now, you'll be surprised how many scalar quantities you know and use, and I've already used one this show. All right, we're also going to investigate vectors and their difference from scalars. So now, I know that I've got scalar quantities, but now there's this new word, vectors. So we're going to start comparing scalars with vectors, and that's going to be something new. Okay, so some of you might say, Phil, I already know what vectors are. Guys, even the matrics should be watching this and learning something new, because I know that this is one of the skills that the matrics are currently struggling with because they forgot what they learned in grade 10. Guys, what we're learning today is something which you can apply right up into university-type engineering, into medicine, anything which uses quantities, and that's just about any type of science. Okay, so the difference between a scalar and a vector. Now, here's something of particular interest, is I'm going to show you how to do one vector after another vector and after another vector, and at the end, we're going to look and see what we have. We're going to take a look at how to do simple addition of vectors. Now, we're going to use some graphical and some calculation methods. Okay, but really don't worry, don't get too far ahead of yourself. All I'm going to do is I'm going to show you how to draw a couple of arrows, how to put the arrows together, and hey, voila, we've got some vector addition. Guys, please don't be intimidated by some of the language that we're going to use today. If you are feeling a little bit intimidated, guys, get on the page. There's notes there. It's got a glossary. It's even got some terms inside there which can help you. In fact, it's got summaries of the notes that are on my screen behind you, and you can actually follow us as well. So get onto our Facebook page, follow the link, get our notes, and follow through with us. Okay, so let's start jumping into some of the quantities that we can start deal with. And here we go. So first of all, what is a quantity? Now, a lot of you have heard this word quantity before, but you're kind of like, it's something that my math teacher says, or it's something that my science teacher says. Let's actually start to deal with the word quantity. Now, quantity is anything which I can measure which uses numbers. It's all about the numbers. Now, earlier on, I started talking to you about how many Facebook likes we had. How many was it again? 50,000?
It's 50,079. Not 500,000 though. I'm just still too ambitious.
Okay, well, we're going to get there. We're going to get there. Just
Soon.
bring your family, bring your sisters, brothers, mothers, whatever. Just bring them and get the page liked and spread it out on Facebook. Even share our page. That would be great. Okay, so now we're going to start dealing with quantities, and quantities is what it's all about here. Now, a quantity is anything which you can describe in terms of numbers. So I'm going to give you some examples. I mean, you can talk about 40 girls, 50 boys. You can talk about 2 lumps of cheese. Anything you can put a number to is a quantity. So guys, you've been dealing with quantities your entire life. Now, anything which I say, okay, well, what is the quantity of mass? What is the quantity of my weight? These are numbers which I start to talk about. How many days until the weekend is something you're asking yourself. That is a quantity itself. It's something which I can measure with a number. So anything with numbers is called a quantity. Now, you might hear this a little bit later on in science, but when you start to talk about quantitative, now that's a lot of syllables. Okay, let's talk about this word, quantitative. Quantitative means to measure using numbers. So when you do a quantitative analysis, or if you talk about a quantitative theory, it just means that I'm trying to find out how much of something I've got. So now here we go. We start to take a look at our numbers, and it's how much we have of this quantity. Now this is a word which is infamous. Guys, it scares matrix, and it really doesn't have to. Here it is. The quantity, and this is my magnitude. That's how much I have of something. So now if somebody walks up to you one day and you say, you know, what is the magnitude of, let's say, for instance, the distance to school, and you start to scratch your head and you say, okay, well, I don't know what you're talking about. It sounds like magnets, and what's that got to do with school? Magnitude is how much I have of something. So your magnitude is just the size of your quantity. So anytime you start to talk about magnets, it just means how much, guys. All right, so I would like to have a large magnitude of money in my bank account one day. So that's one way to start striving for this. Guys, you should strive for a large magnitude of marks at the end of the term. It's just talking about how much I have of that particular number. Now, at all cases, I'm going to be running you through a couple of examples, explaining some of the words again. So don't worry about scribbling down furious notes. Let's start taking a look at some of the other words here. Okay, now this is something else which a lot of people don't pay enough attention to. Anytime I've got a magnitude, there's something that comes after this, and that is the question of units. And you might say, okay, well, sure. Phil, just slow down on the language here. Magnitude is how much I have. A unit is what identifies what magnitude I'm talking about. Now, let me give you a little bit of an example. If I was to walk up to you and I was to say to you, I have 15, and immediately your mind starts to go, okay, well, you got 15 what? 15 of chickens, 15 of eggs, 15 of cars, I hope one day. But start to think about this. You need to give a unit, and in all of those, I gave a unit. Oh, I have 15 kilograms of something. If I have 15 kilograms of sand, I can build something. 15 bricks. What I've been doing is I've been identifying what I'm talking about. So units are unbelievably important. A lot of grade 10 say, I don't have to substitute them, I don't have to put them down, it's not an issue for the calculation. But guys, units tell me what you've got. If I see an exam paper in front of me and I just see an answer with just a number, I cannot give that answer correct tick without a correct unit, because I have no idea what that number is. If somebody says to you, no, the answer is equal to 1, okay, well, that might be useful for simplification in maths, but if I'm talking about some children, it would be really nice to know if I have a whole person or if I've got half a person, which is very bad. Okay, so now let's start talking about the magnitude and how they deal with units. So let's start taking a look at an example of a quantity that we all use. Guys, you already have been dealing with this quantity, and all of us do all day, every day. Okay. So let's start taking a look at what we've got in terms of a quantity. My example, because it's probably the most common example, is this stuff, time. Guys, the clock is always ticking. It's something which I'm always short of. I describe it in many ways. I govern my day by time. This is the reason that I've chosen time as my quantity. I can measure time using numbers. Guys, if you lift up, look at your watch, look at your cell phone, you can measure the time. You've actually got a time measuring device in front of you. Now, let's take a little bit of a step back and let's start to see how we would actually describe what time is in front of us. So if my sister or my brother or my mother or father come up to me and say, Phil, what is the time? Or how much time do I have left? Or how long should I cook this pasta or this egg or this toasted sandwich for? Right. What I can do to them is I can say, okay, well, you need this much time. Now, in physics, what we've got to do is we've got to get a little bit more specific. So now I'm going to introduce you, if you haven't already, guys, I'm going to introduce you to the little bits and pieces of the way that we use quantities in physics. Okay, so first and foremost, you might say, okay, well, Phil, there's a lot of letters over there. I thought I was looking for numbers. There's two different letters over here. One letter over here on the left, and one letter over here on the right. Now you might say, why are there two different letters? This is very confusing. Let me explain this. Okay, now my symbol represents the quantity that I've got. T is for time. Okay, now you might say, okay, well, I don't have 350 times. I've got something in terms of units, and that's what the other number is for. On the right-hand side here, I've got S, and that is for seconds. Now that identifies that I'm dealing with time. So if I was to walk up to you and say, how long is this meant to take? 350 seconds, you would understand what I was saying. Kind of an unusual length of time, but in physics this is quite common. Now let's deal with the difference between these two. Now when I see an equation, I'll use a symbol. This is the thing which I put into an equation, and this is the thing which I find in time equations. How I give my answer or how I deal with the actual magnitude, I use my unit. Now let's get to the really important part of what's on your screen at the moment. The 350, this tells me how much I have. Now if you remember a little bit earlier on in this show, I used the word magnitude to show me how much of something I actually have. How many seconds do I have? I have 350 seconds. This might seem, oh, Phil, this is really simple. But you wouldn't believe how many matrics still ask me, what is the meaning of the word magnitude? So if something is of great magnitude, there's a lot of it. There are many seconds. It has a great magnitude. So I want you to get comfortable with the language as we go, because I'm going to start throwing it around quite quickly. I want to make sure you stay with us. So let's just go through this again. All right, I use a symbol to tell me which quantity I'm dealing with. I use a number to tell me the magnitude, and then I use a unit to identify what I'm measuring in. So this tells me that each one of these 350 pieces is 1 second big. This is why it's called a unit. That is the smallest size that my magnitude can go. Now, very often you'll find decimals of magnitudes. That doesn't necessarily mean that you can't go below 1. It just means you've gone smaller than 1 unit. Now, we'll deal with those when we start to cover motion, but this is something that I want absolutely sure, is that people can lay out their symbol, their magnitude, and then their units. Okay, so now let's get stuck into some of the units that you might remember. I'm going to put something on the screen, and I actually want you to work this out, especially if you've downloaded the notes. I want you to start working out what the missing pieces are. Okay, so we're going to start off here. Now, I'm going to introduce a new word before we begin our table. I want to know what a scalar quantity is. Now, we've actually already dealt with a couple in the show tonight. Now, when you deal with a scalar quantity, that's something which only has magnitude. Now, you might say, okay, that's a little bit weird. You know, what else can a quantity have? I mean, really, you can just count how many or how much of something you have. It's not as simple as that. I'm going to give you examples of things which are scalar quantities. And we're going to start to deal with these. Okay, now, we're going to start off with the example that I started you off on. And that was the one of time. Now, it's quite important when we start to deal with quantities that we know their symbol and their units. Now, time has a symbol of t, so we dealt with that a little bit earlier on in the show. And what about its unit? The SI unit is seconds. So this is a standard unit that I use to measure time. You'll notice that scientists very often will say, okay, well, it's measured in 3 hours and 15 minutes, but guys, hours and minutes don't fit very nicely into equations. I wonder if you can think about why. I think that should be a bit of a challenge question. Why can I not put hours and minutes in equations that ask for time? I want you guys to think about that for a second, and after an ad break, I'm going to come back and answer your question. Post on the Facebook page so long. Then, what I'm going to do is I'm going to set this up as a little bit of a challenge. I've left some spaces out. Okay, now I'm going to deal with some of these quantities over here, some of these things which I can measure. Now, all of us up here in the Highveld at the moment are very aware of this thing at the moment. And in fact, all the way across the country, temperature. Temperature is something I can measure. And it's something that I listen to the newspaper reports and, into the radio reports. I don't listen to my newspaper. And I watch the TV and I want to know what is the temperature, how much temperature do I have? I don't have a lot of temperature at the moment. I measure it in degrees Celsius. But guys, can you guess what the symbol is? You can see that there's something missing over there. Right now, grade 10s, even if you understand what a scalar quantity is, I want you to go through and try and figure out if you understand what these missing units are. So there's quite a few that appear on here that we've actually started to deal with throughout this year, and you might have seen in class. But what I'm going to do is I'm going to leave that as a little bit of a challenge. When we come back from the break, guys, why can't we deal with minutes and hours in equations when we deal with quantities? And it's quite important. This just puts emphasis on the units. What do you think? I think it's time for a break, eh?
It is indeed, and we're going to leave them with that question, as they say that time and tide waits for no man. So after the break, we'll get to the challenging question and see your answers of our Facebook page. But for now, take that time and work on the challenging questions. We'll see you after this break. Welcome back, Mindsetters. I hope now you've got the challenging question and you have the right answers. But before I take your questions over Facebook, remember you can get the notes also on our website, which is learnextra.co.za/live. I have the fast link posted on our Facebook page. So get on over Facebook. Our Facebook is facebook.com/learnextra. For now, Phil, before I take your questions, you've got some exciting news to share with the Mindsetters.
Oh, what is that?
About the Curio.
Oh, okay, absolutely. Well, guys, you know what Curio is. Get onto it. The link is on our page. And guys, the code for today is PS10. So for those of you that don't know what Curio is, jump on our Facebook page. It's all there. Abam's been posting away and he's posting up the link. Guys, get on there. There's a couple of multiple choice questions which you can answer. Now, please, when you do these, make sure you do them properly. Give them a proper try and click submit. If you skip through the questions, unfortunately, it's going to look like you can't do your questions. So make sure that you try every question and click submit at the end of the questions. So make sure that you get onto there. Just a reminder, the code for today is PS10 when you log on to Curio on Mixit. Fantastic.
Now
Shall we go on?
Yes, on the question that we asked, remember we
Oh,
asked
good.
the
What have we got
Mindsetters,
there?
We said, why can't we use hours and minutes in scientific calculator?
Yes.
And then there are two answers that I got from Tami Chiretusi. He says, I think we don't use hours and minutes in equations because they can be divided further, e.g. 1 hour is called to 60 minutes and 1 minute is called to 60 seconds.
Yes.
And another one is from Aphiwe Morgan Makatini. He says 1 hour has 60 minutes, so they don't correspond.
Absolutely, guys. Minutes and hours really do not correspond. Science operates on decimal system. Now, let me just give you a little bit of a confusing fact. When you start to talk to somebody about 1.5 hours, now your mind's already starting to convert that into things. Now, in terms of the decimal system, 1.5 hours is equal to 90 minutes. Now, guys, that really doesn't make any sense to any of the other units in science. When you start doing conversions of 60 instead of 10, like the rest of the decimal system, things go horribly wrong. And those guys are absolutely amazing for getting the answer right. You can divide hours and minutes by multiplying by 60 and multiplying by 60 again. Guys, 60 doesn't fit into the normal decimal number system, which uses 10. So timesing and dividing by 10 is how the rest of the number system in science works. I can do that with seconds, but guys, I cannot do that with minutes and hours because I've got this really strange 60 thing. Now, the reason that those 60 things exist is because of the rotation of the Earth and degrees. So if you want to do a little bit of investigation and maybe sharing on the page, you can start to talk to us about why an hour is an hour long, or why it's got 60 minutes inside it, or why that's got 60 seconds inside that. So really nice question over there. Okay, so, all right, now we're getting back to this. And I wanted to chat to you a little bit about some of these units. I hope that the guys at home, the mindsetters, are busy dealing with some of these quantities over here. Now, I particularly like this temperature one. I'm looking forward to springtime when the temperature increases. I want a greater magnitude of temperature. The symbol, and this is why the symbol is so important, guys, is a T as well. The reason that I've chosen time and temperature is that they both have a T, except temperature is a capital T. Okay, now we're getting into the ones that you guys have already seen before. I know that all of you guys have been doing distance, speed, and time calculations, especially in maths. In grade 9, you were starting to deal with distance, speed, and time. Now, I just want to remind you guys, this is not a maths lesson. All that I'm doing is reintroducing some of the units. Okay, so now we all know what distance is. Distance is how far I go. Now, how do I measure this, or how do I put this into an equation? Well, the symbol that I use for distance is D, a capital D specifically. All right, but now what is the unit? How do I measure how far I go? Now, the standard unit that is used inside physics is 1 meter. Okay, quite similarly, we can start extending our use of scalar quantities right the way down this table. You'll notice that speed is missing a symbol. So what is a symbol for speed? That would be an S. And that is measured in meters per second. So if I say I'm moving at a speed of 5 meters per second, that's what I would substitute in place of S for that formula. So it's absolutely vital that you know that both the symbol and the unit for all of these scalar quantities. Now, if you're a little bit confused as to why I'm calling them scalar quantities, I'm going to make that a little clearer. I know that all of these are scalar, but some of you are a little bit unsure about that word scalar. Okay, now we've got to start doing a little bit of investigation work over here. Something which has a symbol M, that's a bit of a clue. And what about its unit of kilograms? Okay, now guys, I know what some of you are thinking. And this is something which I do very often in the morning, especially if I'm feeling a little bit conscious about what I've eaten or how much exercise I'm getting. I start to measure my kilograms in my body. Now, you might actually start to think about this, but Phil, how do we do weight in here? Now, guys, weight is not a scalar quantity. So what is this thing with the symbol M? It's mass. Now, you might ask yourself, but Phil, I weigh myself on a scale in the morning. Now, what you'll actually find is that that scale is using your weight to find out your mass. Now, if you're not sure about the difference between those two, stick around and we're going to show you the difference. Okay, now this next one, I know for certain Tracy was talking all about moles last week. And you guys are going, Phil, wow, we're in a physics lesson, please. Let's try and keep this away from the chemistry. But guys, it's also a scalar quantity. It's something which I can measure, and there is actually no separation between the sciences. They always will overlap. Okay, what are moles and how do I represent them in an equation? I hope that you remember that you can measure moles with the symbol N, and there we go. I've got a unit of MOL. So what I've got to do is remember my symbol and my unit. Now guys, I challenge you to go find some more scalar quantities. I'm going to leave a little bit of a spot here, which we can fill up a little bit later. I actually want to hear from you on the Facebook page and find out what is another example of a scalar quantity, and then we can get into some dialogue about what is and is not a scalar quantity. All right. Now what we're going to do is we're going to clarify what I meant by scalar and vector. Now, some of you might have watched a movie recently and saw that vector was actually an evil villain. Okay, now vector is a scientific quantity. It's also something which I can measure with numbers. So a vector is something which has also got magnitude, but this is the really special thing. A vector quantity has got magnitude, and this is the really, really important thing, direction. You might say, okay, well, how do you put in a direction into a unit? I mean, do you just say temperature here, have some direction? No, absolutely not. Okay, what you've got to do is you've got to realize that some units need direction to give them some sort of meaning. Now, here's an example for you. This is just to give you an example of why direction is so important. If I tell you to stand up and walk 50 meters, you're going to say, oh, well, that's not going to work. if I stand up from my couch or from the floor or from the table where I'm watching TV at the moment, I'm going to bump into things. And where should I go once I get out the door, if I get out the door? Direction means a lot, especially when we're starting to move. And guys, next week, it's all going to be about motion. So it's vitally important that some units have got direction. It might actually surprise you which units have direction in them. Now, what I'm actually going to do is I'm going to discuss the symbol, the unit, and how I describe the direction. Now, you might say, okay, well, I can see this for distance. Okay, stand up, walk 50 meters forward. All of a sudden, no longer are we talking about distance. It's a separate unit. It's no longer distance. It's displacement. And we're going to talk about these words in a moment, especially next week when they become important. So now, let's start to talk about that one, which some of you are a little bit afraid. I see that bathroom scale in there in the morning, and I sort of climb on, and I close my eyes, and I hope for the best, and I look down. What am I measuring? A lot of you think, okay, well, I'm measuring my weight. But guys, what's on the scale is measuring kilograms. This is very confusing. Now, this is where some of the confusion comes in. If I say that I have a large mass, I also have a large weight. But now, what is the confusion between these two? Now, weight is a force, guys. Weight is how strongly the earth is attracting you. There we go. So weight is a force, and sometimes it's Fg. And you might say, why is it not W? Now, we're trying to move away from W for weight for one simple reason. It's because there's another quantity which also has the symbol of W, and that is work. So these things can get very easily confused between the two. So it's better to say force, gravity. Now, the force, gravity, has got a unit, and you might say, okay, well, I don't have a weight down. But guys, absolutely you do. This is one of the reasons when I fall out of bed that I fall down. The direction of weight is always towards earth. It's always down, wherever down is for me. So weight is an example of a vector quantity. I feel a certain force down onto earth, and it's always in a certain direction. It's very important that it has direction. If I fell upwards, we'd all fly into space. Weight definitely is a vector, guys. It has a magnitude, which I can measure in newtons, and I can describe that it's a force downwards. I hope that you can see the difference between a vector quantity and a scalar quantity. Now, all quantities can be separated into those two things. Ones without direction can be classed as scalar. So they're just things which I measure up with numbers. I'm just going to go back to that spreadsheet that we were talking about a little bit earlier on this table. All of these didn't need direction. Now, if I was to say to you, okay, well, if I say to you, I need 15 moles of sulfur forward, you'd be very confused. Okay, I'm confused saying that. If I say to you, I go 15 seconds up, it's a very strange thing to attach direction to any one of these. And if I say to you, okay, it's 5 degrees to the right today, and a lot of you are saying, okay, well, I'm not dealing with trigonometry here, I'm talking about temperature in Celsius. All of these don't have any direction. This is what makes them a scalar quantity. Scalar quantities don't have a direction. Now let's take a look at some of the other vectors. I hope that you guys are filling in ahead of me. These vectors have all got directions. Now we're going to fill this in together. Displacement has got an unusual symbol, and that's a symbol of x. Now you might say, okay, well, Phil, why does displacement, and what is displacement, and why does it have this strange symbol of x? Okay, well, distance is the cousin of displacement. So displacement and distance go together. Now, if I say to you, stand up and walk 5 meters, what I've given you is a distance which I want you to walk. I haven't told you where. So that is a distance. When I deal with displacement, I need to add a direction. If I was to say to you, okay, well, stand up and walk 5 meters towards the fridge, all of a sudden now you've got a place to go and you know exactly where you're going. And that is displacement. But again, why the symbol x? Why am I using x to describe displacement? Well, guys, think about maths. When you've got a flat Cartesian plane, the x-axis is the horizontal one. Now, sometimes things move up and down, and I describe their displacement as y. So now we'll get to y later on and perhaps even next year. But displacement in terms of x just means how far did I move across the ground. Now this is the important part, in a particular direction. That makes it into a vector. Now this next one, you might recognize this, but before we go there, let's talk about displacement's unit. This tells me that this is related to distance and it's measured in meters. Now velocity, I see has got a unit which I've seen before. I can measure velocity in meters per second. That sounds a lot like speed. However, the difference between velocity and speed, I'm hoping that you've managed to guess it, is that speed is a scalar, while velocity is a vector. Now, if I was to say to you, I was heading at 50 meters per second, that's very, very fast, 180 kilometers per hour. If I was traveling at 50 meters per second, and you say, okay, well, where were you going? The minute I add direction to it, it becomes a vector. If I said I was moving 50 meters per second towards the coast because I wanted to go on holiday and I got pulled over by a speed cop, that's very, very dangerous. But this velocity over here is measured in the same units as speed. However, I need to add a direction. So all of these need to add direction. Now let's deal with this next one, acceleration. Most of you have dealt with that before. Measured in meters per second squared, also needs direction. Now, some of you might say, okay, well, I've never dealt with acceleration before. Now, most of you have picked up an object before and dropped it to the ground. Everybody has done that. An object which was stationary in your hand started to accelerate towards the ground. Now, I challenge you, and I really, really do challenge you. I want you to discuss this on your page, to try to find an object which accelerates in the opposite direction to gravity that doesn't have an engine or a motor or something pushing it upwards. So most objects, I mean, the saying goes, what goes up must go down. Now, if I launch this thing up, it's going to go down eventually. Gravity always acts in the same direction, guys, and that is its acceleration acting. The acceleration of objects towards the Earth is a constant. Okay, and then this next one. This is a word which we're going to say for next year, but momentum as well is dependent on velocity. Now, the only reason that I put in momentum is because momentum is the amount of motion that something has. That also depends on the direction of this motion. So, guys, I'm going to leave a couple of empty spaces there. I want your suggestions about vector quantities. Ask me, is this a vector quantity? Fish things out of your textbook. Take a look, even in your biology or history, geography. Start looking for numbers, things with units. Post them on the page, and we're going to discuss, are they a scalar or are they a vector? Guys, I think I'm going to let you have a little bit of a break. Maybe think of some examples over there.
And I have your answers also on what are some of the examples that we may not have on the table for
That's fantastic.
Yeah, we'll take them after the break.
That's great. Guys, keep adding.
Right. And also, Mindsetters, after the break, I've got some exciting news that I need to tell you. So don't move. See you after the break. Welcome back, Mindsetters, and now, as promised to you, Mindset is looking to hire someone, and we need your help. If you know of anyone who would be interested in doing our grade 10 to grade 12 CAPS aligned content development, video presentation, and also review of that content, make sure that you go to mindset.co.za/land/jobs, and that's where you can get more information. The closing date is the 26th of August, so get all the information out there, and let's help other people get a job, because we're looking to hire someone. But now, Phil, on another note, we need to take some of the examples that we have from the Mindsetters.
That's fantastic. Let's do that.
Right. The first example that we have is from Apua Morgan Makatini. He says electric charge.
Electric charge is an excellent one. Now, one of the things that I need to do is to say, okay, well, I've got electric charge. Let's say I've got 2 coulombs. I don't put a direction on it. That should tell me that electric charge is a scalar quantity. So let's actually write that in. So if you guys are adding to this, so electric charge is a really nice one. So electric charge. All right, so now what I'm going to do is I'm actually going to give you the symbol. The symbol is Q, but the unit is measured in coulombs, which is C. Are there any others over there?
All right, another example from Jabula Brian is volume, time, speed, and power.
Okay, well, we've got speed, we've got time, but what about volume and power? Okay, so volume is a really nice one because it's not one that I commonly come across, but volume with a symbol V, with a unit of meters cubed. Very, very nice. And then power, of course. Okay, now all of these are scalar quantities. These are things which don't have any direction. Power, symbol P, and then the unit, of course, is W, which is watts. Very, very nice.
And
Are there any others there? Yeah, let's do it.
Lebogang Dumi says work.
Ah, work. Now, work is an interesting one. You usually measure work in joules, and it's a measure of energy, which is also a scalar quantity. So when you start to deal with work, which is measured. Now, here's the symbol W. This is why we don't use W for weight. So work, which is measured, its symbol is W, and its unit, I think I've just thrown my W off the screen there. Let's bring back the work. I know you guys are working nicely at home. All right, so there we go. My unit over there is joules. Very, very nice. Okay, that's a lot of scalar quantities. A lot of people are staying away from the vector quantities. Let's make it a little bit less scary. Okay, now guys, most of you have started to deal with electric charges. Now, notice that some of you even suggested electric charges. But what about electric field strength? Okay, so electric field strength is a very good example of something which is a vector. So the electric field strength, so I'm going to abbreviate it here because I'm running out of space on my table here. Electric field strength with the symbol of E. Now, its unit is newtons per coulomb. That's how many newtons each coulomb will feel in a particular space. Why is it a vector, guys? Well, first of all, it's got a magnitude which I can measure in newtons per coulomb. And, guys, this is the most important thing. Electric field has a direction, away from plus towards minus. Remember that electric field strength you decide using a positive test charge. Okay, so I'm going to leave it out there. I want to just give you a little bit of a chance to suggest some more vectors. But now let's start
There's
dealing.
one last more.
There is?
That's
fantastic.
Twanela says force.
Force. Excellent. Now, guys, forces are so, so important. Now, we've dealt with one particular force, but force in general with symbol F is also measured in newtons. And the reason that it's a vector is if I say I'm pushing with a force of 50 newtons, I need to say where I'm pushing this object to. So really nice, guys, that you're suggesting your own versions of scalars and vectors. Okay, so we've filled up our tables. Now let's do something with my vectors. Now, guys, this is really important. How do I represent a vector? And the answer is really, really simple. I need something that can change its size or its magnitude and can point me in a certain direction. Now, guys, what I've just described is an arrow. Now, if you can draw an arrow, you can draw a vector diagram. A vector diagram is just a whole bunch of arrows to represent the vectors. Now, these have got a little bit of a bad reputation, and they don't need to because it's really simple. Guys, I want you to get a ruler and a calculator and sit tight because we're going to help you draw vectors. Okay, so now, why do I use an arrow? Well, it's very easy to see why. Because they can represent magnitude because of how long they are. So a shorter one has less magnitude. A longer arrow will have more magnitude. And then they also show direction. That's the most important part. I can point anywhere I want using an arrow. So all I have to do is point it in the right direction. So now what I'm going to do is I'm going to hold your hand. We're going to draw our first vector together. And I'm going to show you all about direction. Now, direction is a little bit of a tricky thing. And I noticed from the Curo page results that some of you are battling with directions and bearings and all sorts of fancy terms. Just hang on a second. We'll explain it in a moment. Okay, so here we go. Now, it says someone walks 30 meters to the right. Now, I don't particularly like what we've done here, to the right. Now, I say to the right. Who's right? My right, your right, there are different rights. So this is why very often you won't actually see this. But what I'm going to pretend is that we're talking about right on the page for the moment, and then we'll introduce more complex ways of doing things. Now, the question is, how do you draw 30 meters with a tiny little ruler? Okay, guys, I want you to grab your ruler and you're going to work with me today. Okay, here's the important thing. I need to work with a scale. My ruler draws in centimeters, but I need to represent meters. So if I draw a line which is 1 centimeter, I can show that I've got 10 meters as a vector. What about 30 meters? How on earth would I get 30 meters? Well, you guessed it. If 1 centimeter is 10 meters, 2 centimeters is 20 meters, 3 centimeters represents 30 meters. Now, they do get a little bit more complex. If you struggle with the ratios, I'll help you. Okay, so now we're going to get our ruler, and we need to position it correctly. So let's just make sure that my ruler is nice and flat. Now, first and foremost, I want to make sure that I'm going to be able to draw an arrow. Give yourself a little bit of extra space because sometimes there's other vectors which come onto my page. I'm going to draw a nice arrow. So first of all, what I want to do is I want to point this arrow. Now let's just make sure that my arrow is going to be nice and thick on this page, and we're going to deal with an end which is ending in a normal arrow. So what I want is something which looks like that. Now the problem is, let's actually make that a solid line. Let's make sure that everyone can see exactly what I'm doing, because you guys are going to be drawing a solid line. There we go. I'm going to pick a solid one. There we go. And there we are. Okay, so let's just make sure, let's make that nice and visible. Make yours nice and visible as well. So what I'm going to do is I'm going to start picking my arrows here. Now just a reminder, I don't know where this arrow is going until I've picked a head for this thing. So I've got to make sure that I'm drawing a completed arrow as it goes. Now this arrow is the wrong size. You might say, Phil, that doesn't represent 30 newtons. So what do I have to do? Let's go back and let's fix up what's going on with my arrow. In fact, let's try to see if we can't get a slightly different color. I don't like that pink. It's not nice and visible for you guys at home. I want to make sure that I can do that. All right. And then let's actually start to experiment there. There we go. That's a nice little arrow. I'm going to scale it up and down. Okay. So now I've got my ruler in front of me, and I know that I want to draw something which is 3 centimeters long. So I start out, and I draw all the way down to 3 centimeters. I don't know if you guys can see, but I've broken my arrow there a little bit. Let me just start again. So there we go, all the way down to 3 centimeters, all the way to the right. This is pointing right. Now please, when you do this, make sure that you're labeling everything. So there we go. I mentioned that this represents 30 meters. You don't write down 3 centimeters. Anybody can measure it on your page. You mentioned the real size of your vector. Now, there it is. All that we had to do was draw a 3 centimeter line and call it a 30 meter vector. Now, that is how to draw a vector arrow. That really wasn't too complex. But now, things get a little bit more complex. We're going to start dealing with examples which start to introduce multiple vectors. So now, I don't just walk 30 meters in one direction and that's where I stay. Guys, you tend to walk around. You'll find that you do multiple things one after the other. Now, what I'm going to show you now is called the head-to-tail method of adding vectors. So a lot of you on the Cura page are really struggling with this. Now, you can join up arrows one after each other. The head of one arrow should meet with the tail of the other. So now these arrows have to be joined, and this is actually the name of the method. It's called head-to-tail. That means the tail of one should start at the head of the last one. Notice how those two arrows are actually touching each other with the head of one and the tail of the last one. Then we find the distance from the beginning of the first to the end of the last arrow. Now that sounds hugely complicated, but I'm going to use these two little pink arrows and I'm going to draw in a green arrow. The green arrow is going to represent what we achieved. What was the end result of what we did? That meant that I ended up somewhere over here. If I walked up and to the right, I would have ended up in the place where the green arrow is showing me. But I can't leave it like that, guys. You've got to be a lot more specific. Now, this green line is called the resultant. The resultant is the end sum. When you've added together all the vectors, the resultant is what comes out. Now, guys, I know that some textbooks say sometimes the resultant, you've got to subtract things. Guys, the resultant is always a sum. It's the total of all of your actions. If I walk 2 steps forward and 1 step back, what is the total of my efforts? Now, what you'll find is you'll say, okay, well, that's 2 minus 1. That means that I land up 1 step away from where I was. Okay, you're doing that mentally. Now, let's do this graphically together. Okay, so now I'm going to introduce the idea of different types of direction over here. So I got my ruler ready. I hope you've got this right. But now, I've got a major problem over here. It says that someone walks 30 meters north and then 40 meters east. There's 2 vectors. How do I do that? Well, guys, I've got to use that same scale again, and I've done 30 meters before. That means that I'm going to draw a line which is 3 centimeters. How do I do 40 meters? You guys guessed it. That's 4 centimeters. What is their final resultant? So where did they land up? So this is what I'm after. This is always what I'm after when I'm dealing with vectors and simple addition. Okay, so guys, I'm going to hold your hand here. The first thing that you're going to do is, because we're talking about north and east, I need a reference of cardinal points. Now that sounds way more fancy than it actually is. What I want you to do when you're trying to do cardinal points is I want you to make a compass. Guys, a compass has got your 4 points over there. Your compass is always your starting point when you've got questions of north, east, south, west. So there's my north, there's my east, there's my south and west. Hopefully you guys have got this down. Okay, but now what I'm going to do is I'm going to use my compass, the center of it, as a starting point. So now this person, if I put my zero of my ruler over there, this person walks 30 meters north. So what I've got to do now is I've got to draw a line which goes up 3 centimeters up the north line. So let's do exactly that. Let's rotate our ruler around so it's facing directly north, and let's draw something. Let's just make sure that's nice and north. It's fighting me today. There we go. All right, so we got a nice north-facing ruler. Now let's draw ourselves a 3 centimeter ruler. So now, I don't know if you can see the numbers on there, but I'm going to actually read them out as I go. I'm going to start out over here, so down at the bottom, I'm going to draw all the way up. Right, so there we go. We've got 3 centimeters drawn up there, and we can move our ruler away. And let's just make sure that that ends in a head to show me that this person walked 30 meters north. There we go. Now what we're going to do is we're going to allow this person from that new position to walk 40 meters to the east. Okay, so now what I've got to do is I don't go back to my start. That's not possible. I can't start from the beginning again. Now what I do is I apply the head to tail method. I've got the head of the original arrow, and I've got the tail of the one that I'm about to draw. So there we go. I've got now a ruler which faces directly east. If you really want to, you can do this with the protractor or that right square inside your math set to make sure that you've got a nice 90 degrees. But I'm just going to do this by eye. But at the moment, I can see that that is starting at the head of my original vector. Now what I'm going to do is I'm going to draw in my new vector of 40 meters to the east. So let's do this. So let's draw in another vector. I've got a vector which starts at the head of the one, follows through. So there's 2, 3, 4 centimeters over there. Fantastic. We've drawn in our new vector. Let's just make sure that there's a nice head on the end of it. Right, and that represents 40 meters to the east. Now the question is, where's the resultant? Now, remember what I said. You start right at the beginning of the story and you find out where the end is. So what I'm going to do now is I'm going to use my ruler to do exactly that. So I'll show you exactly what I'm after. I want to put my ruler where I began. So that's where I start. So this is the beginning of our story, this person that's about to walk 30 meters, then 40 meters. Now I'm going to close a triangle over here. Now, it's not always a triangle, but what you can do now is you can say, okay, I'm going to rotate my ruler around, and I'm actually going to find something very interesting if I do this. And it's not actually all that clear over there. I'm not sure if you can actually read that off there, but what I'm actually finding is that there's a very interesting resultant. It shouldn't be a surprising resultant at all. If I start there, let's make that a nice bright color over there. So we're starting at the beginning there, and I'm drawing in my resultant over there, and I'll measure it, guys. What I'll find is that the length of this one with my ruler, and I'm hoping you're doing this at home, is 5 centimeters. That's very interesting. Why 5 centimeters? Because that works out to be 50 meters. Now guys, I hope that you've seen this ratio of 4 to 3 to 5 before, because guys, this is a Pythagoras triangle, because look, I've got a 90 degree over here. So I can say that my resultant is 50 meters, but now I need to give it a direction. And guys, here's your challenge. You need to measure it from the north. Any diagram where you measure the degrees clockwise from north is called your bearing. I know that this is something that people really struggle with, but when you start at north and you measure clockwise from north, that is your bearing. So guys, I want you to try and state this, and I'm going to look on the Facebook page for 50 meters, and I want the bearing of this, guys. Unfortunately, we're running out of time. I'm just enjoying this so much.
Yeah, well, It is that time again. So it's unfortunate that we have to end it here. But otherwise, if you still need some help, Mindsets, make sure that you go to mindset.co.za/learn and /help desk. We'll be more than willing to help you also on Facebook. But for today, we just want to say thank you very, very much. Don't forget, still take the assessment on curio.co.za. Your code is a PS10. Peace from us. We'll see you